Ever find yourself sweating a little when you're trying to parallel park?
Oh, yeah,
Or maybe attempting a tricky three-point turn on a narrow street?
definitely.
Us humans,
Yeah.
we have our driving weaknesses. But can you imagine a self-driving car
Yeah.
that could handle not just those everyday maneuvers, but even the trickiest situations that you
Oh.
could think of?
Wow.
That's the future that DiMA is pointing to.
Yeah.
And we're going to break down exactly how we've got this fascinating research paper here, distilling multimodal large language models for autonomous driving,
Okay.
plus a whole stack of articles about this new DiMA system.
The real breakthrough with DiMA is how it's tackling this challenge
Okay.
that's plagued self-driving cars from the start.
Yeah.
The long tail problem.
Okay, long tail problem. That sounds kind of ominous.
It is a little bit.
What exactly does that mean in the self-driving world?
So think about all the routine things that we do as drivers.
Right.
Staying in our lane,
Mm-hmm.
stopping at red lights,
Yeah.
following at a safe distance.
Yeah.
Current self-driving systems are pretty good at these tasks.
Right.
Because they've been trained on mountains of data
Yeah.
from these everyday driving scenarios.
Makes sense. Practice makes perfect, even for AI.
Exactly.
But that doesn't sound like much of a problem to me.
Well, the problem arises when you throw in those less common,
Okay.
more unpredictable situations,
Mm-hmm.
the long tail of driving scenarios.
Gotcha.
So let's say you need to make a three-point turn on a busy street,
Oh, yeah.
or navigate a construction zone with all those confusing detours,
Yeah.
or even just figure out how to merge back into traffic from like an awkward parking spot.
Yeah.
These are the edge cases.
Yeah.
And while they're less frequent,
Yeah.
that's where traditional vision-based systems often fall short.
Really?
They might be great at recognizing objects and patterns,
Mm-hmm.
but they often lack that common sense reasoning
Okay.
that we humans use to navigate those trickier situations.
So is DiMA stepping in to provide a little extra street smarts for these cars?
Exactly.
DiMA is all about bringing together the best of both worlds.
Okay.
It combines those powerful vision-based systems.
Mm-hmm.
Think of those as like the car's eyes and reflexes
Right.
with the knowledge and reasoning capabilities of large language models,
Right.
or LLMs.
Now, we've talked about LLMs before on the show,
We have.
but just to refresh everyone's memory,
Yeah.
what makes them so special?
So LLMs,
Yeah.
they're trained on this vast sea of text and code,
Mm.
giving them this remarkable ability to understand and generate human language.
Yep.
They can translate languages.
Yeah.
They can write different kinds of creative text formats
Mm.
and answer your questions in an informative way.
Right.
But what's really intriguing is their potential to reason
Okay.
and make inferences about the world almost like a human would.
So instead of just reacting to what they see,
Yeah.
LLMs can actually help the car understand the why behind the what.
Precisely. DiMA isn't about just dumping an LLM into the car's computer.
It's about intelligently distilling the LLM's knowledge into a system
Mm-hmm.
that works seamlessly with the vision-based components.
Gotcha.
Think of it as creating this highly skilled driving instructor that lives inside the car's brain,
Okay.
constantly guiding and refining its decision-making.
Okay. Now we're getting to the juicy part. How does this driving instructor actually work?
Okay.
Is the car reading like a digital copy of the driver's handbook or something?
That's a fun image.
Yeah.
But no, it's much more sophisticated than that.
Okay.
DiMA works by bridging this gap
Mm-hmm.
between the visual information coming from the car's sensors
Okay.
and the language-based knowledge
Yeah.
stored within the LLM.
Okay.
It does this through something called beam token embeddings.
Beam token embeddings.
Yeah.
All right, that definitely needs unpacking. What exactly are we talking about here?
Imagine the car is looking out at the world through its cameras.
Mm-hmm.
It sees this jumble of objects,
Yeah.
cars,
Yeah.
pedestrians,
Hmm.
traffic lights, trees,
Yeah.
buildings. Now, DiMA's job is to take all that visual chaos
Okay.
and break it down into meaningful chunks of information,
Mm-hmm.
kind of like organizing a messy room.
Yeah.
These organized pieces of information are called tokens,
Okay.
and the beam stands for bird's eye view, ego agent, and map.
Okay, so it's creating like a mental map of its surroundings
Yeah.
and breaking it down by type.
Exactly. The bird's eye view gives the car an overall layout of the scene.
Okay.
From above, kind of like a drone shot.
Right.
Ego refers to the car itself, its position and its movements.
Gotcha.
Agent represents all the other actors in the scene.
Okay.
Other cars, pedestrians, cyclists,
Yeah.
anything that's moving and could potentially interact with the car.
Makes sense.
And map, of course, provides the road layout, lane markings, and surrounding environment.
So DiMA is taking this real-time visual data and transforming it into kind of a digital language that the LLM can understand.
Exactly.
Yeah.
And what makes DiMA even more impressive is that it doesn't just create these tokens in isolation.
Yeah.
The scene encoder, the part of the system that's doing this translation, is actually trained jointly with the LLM.
Wow.
This means that the tokens aren't just static representations. They're dynamically shaped and refined by the LLM's vast knowledge base.
So it's like the LLM is acting as a co-pilot.
Yeah.
Constantly providing context and insight into the scene.
Exactly.
As the car's processing it.
It's this constant feedback loop between the visual and the linguistic that makes DiMA so groundbreaking. Instead of just recognizing there's an object there, the part can start to understand, that's a cyclist approaching an intersection. I should be extra cautious.
Wow.
Or that car's brake lights just came on. I need to anticipate a sudden stop.
That's incredible.
It's this ability to reason about the scene, not just react to it.
Yeah.
That sets DiMA apart.
This is all incredibly fascinating, but we've got to get into the nitty-gritty of how this system actually learns to do all of this.
Okay.
I mean, how do you train a car to have common sense? That sounds like a tall order.
It is.
Even for AI.
Well, you're right. It is a tall order.
Yeah.
And that's where DiMA's training process gets really ingenious.
No, okay.
It utilizes a set of novel surrogate tasks to essentially teach the system how to think like a human driver.
Okay, so surrogate tasks. I'm picturing a car in a virtual driving school.
Yeah.
Learning all the rules of the road.
You're getting the idea.
Okay, good.
DiMA's training isn't just about feeding it endless hours of driving footage.
Right.
It's about presenting it with specific challenges.
Okay.
That force it to use both its visual perception and its language-based reasoning to solve problems.
I see.
These surrogate tasks are designed to build up the car's common sense understanding of driving.
All right, I'm all ears. What kind of challenges are we talking about here?
Well, there are three main ones,
Okay.
each with a very specific purpose. Let's start with the first one, which is called masked token reconstruction.
Masked token reconstruction. Sounds a bit cryptic. What's
Yeah.
going on under the hood there?
Imagine you're trying to piece together a puzzle,
Okay.
but some of the pieces are missing.
Yeah.
You have to use the surrounding pieces, the context,
Right.
to figure out what should go in those blank spaces. That's essentially what's happening in masked token reconstruction.
Okay.
DiMA randomly masks or hides
Yeah.
some of those beam token embeddings we talked about.
So it's like giving the car a vision test.
Kinda.
But instead of letters on an eye chart, it's missing pieces of its mental map.
Exactly. And then the LLM has to step in and try to reconstruct those missing pieces
Okay.
using the information it has from the remaining visible tokens.
So by filling in the gaps,
Yeah.
it's not just learning to see,
Right.
it's learning to understand the scene.
Precisely. This process forces the LLM to develop a deeper understanding of how different elements in the driving environment relate to each other.
Yeah.
It has to learn to infer what should be there,
Okay.
even when it can't directly see it.
Right.
That's a key part of common sense reasoning.
That makes a lot of sense. What about the next surrogate task?
Okay.
Future BEV prediction. What's that all about?
Think about how, as experienced drivers, we're constantly anticipating what's going to happen next on the road.
Yeah.
We don't just react to what we see at this very moment.
Right.
We're thinking a few steps ahead, predicting how other cars might move,
Yeah.
anticipating potential hazards.
Right.
That's exactly what DiMA is trying to teach the car to do with future BEV prediction.
So instead of just seeing a snapshot of the present, it's learning to create a short film of what it thinks will happen next.
Exactly.
Like a precog for self-driving cars.
That's a great analogy.
Okay.
By learning to predict future states of the scene, even just a few seconds into the future.
Yeah.
The system becomes much better at making proactive decisions.
Okay.
It's not just reacting to what's happening right now. It's already thinking about what might happen next
Right.
and adjusting its behavior accordingly.
Okay, so masked token reconstruction helps the car understand the current scene.
Right.
Future BEV prediction helps it anticipate what might happen next.
Exactly.
What about the third surrogate task scene, editing?
Okay.
What kind of editing magic is going on there?
Scene editing is all about helping the car understand how the actions of other agents in the scene might impact its own driving.
So it's like the car is learning to play a game of what if with the driving environment.
Exactly. DiMA will digitally add or remove virtual agents in the scene.
Okay.
Another car merging into the lane, a pedestrian stepping off the curb,
Gotcha.
a cyclist swerving to avoid an obstacle.
Yeah.
Then it asks the LLM questions about how those changes would affect the ego vehicle's behavior.
Wait, hold on. The car is actually being quizzed on these hypothetical scenarios?
It is. And this questioning process is crucial.
Okay.
It forces the LLM to not just observe the changes, but to actually reason about their potential consequences.
Okay.
This is how DiMA moves beyond simple pattern recognition and starts to develop a true understanding of cause and effect in the driving world.
So by the end of all this training, it's not just reacting to what it sees. It's understanding the dynamics of the entire driving environment.
Exactly.
But how does all this knowledge that the LLM has learned actually get transferred to the vision-based planner, the part of the system that's making those real-time driving decisions?
That's a great question, and it gets to the heart of what makes DiMA so innovative.
Okay.
It's not enough for the LLM to just be a brilliant student.
Yeah.
Acing all these surrogate tasks, it has to be able to pass on its wisdom to the vision-based planner, which is ultimately responsible for controlling the car. This process is called knowledge distillation.
Knowledge distillation. I like the sound of that. Is it like the LLM is giving a crash course?
It is.
In safe driving to the vision-based planner?
That's a perfect way to think about it.
Okay.
DiMA doesn't just use the LLM during training. It actually transfers the LLM's knowledge to the vision-based planner.
Okay. But practically speaking, how does that work? Is there some kind of digital mind meld going on here?
It's not quite telepathy, but it's pretty remarkable.
Okay.
DiMA guides the vision-based player to learn from the LLM's responses and adjust its own internal models accordingly.
Okay.
Like the LLM is highlighting the most important lessons from its driving school experience and making sure the vision-based planner internalizes them.
So by the end of this whole process, the vision-based planner isn't just relying on its own limited visual data. It's been enriched by the LLM's vast knowledge and reasoning abilities.
Exactly. It's like the vision-based planner has been given a superpower upgrade, a whole new level of understanding and awareness of the driving world.
All right, so we've covered the long tail problem, the magic of beam token embeddings, and these ingenious surrogate tasks.
Yeah.
But let's get down to brass tacks. Does all this fancy training actually translate to better driving in the real world?
Okay.
Did DiMA pass its driving test?
The researchers put DiMA through a battery of tests using the nuScenes dataset, which is considered the gold standard for evaluating self-driving performance. Think of it as like this giant virtual proving ground, packed with all sorts of challenging driving scenarios.
And the results, drum roll, please.
DiMA blew the competition out of the water.
Really?
We're not just talking about incremental improvements here. We're talking about a significant leap forward in self-driving capabilities. Across the board, DiMA showed a 37% reduction in trajectory error.
Okay, for those of us who aren't self-driving engineers, what does that mean in practical terms?
It means the car's planned path was much closer to the ideal path it should be following. Resulting in smoother, more predictable, and ultimately safer driving.
That's impressive. But what about the ultimate measure of safety? Collisions. Any improvements there?
Hold on to your hats, because this is where it gets really exciting. DiMA achieved an 80% reduction in the collision rate.
Wow.
Compared to traditional vision-based systems.
80%? That's incredible. What's driving those dramatic improvements?
It's a combination of everything we've talked about. The LLM's ability to reason about the scene, the surrogate tasks that build up its common sense, and the knowledge distillation that infuses that knowledge into the vision-based planner. It all adds up to a car that's not just reacting to the world, but actively anticipating and mitigating potential hazards.
So it's not just about avoiding accidents. It's about creating a much safer and more predictable driving experience overall.
Exactly.
But what about those long tail scenarios we talked about earlier?
Oh, go
The
ahead.
ones that really trip up these self-driving systems.
Yeah.
Did DiMA show any improvements
I
there?
have the most compelling part.
Okay.
Remember those tricky situations that even we humans sometimes struggle with?
Yeah.
DiMA showed the most dramatic improvements in those very scenarios.
Really?
The researchers specifically tested it on a three-point turn,
Okay.
which is a notoriously complex maneuver for autonomous vehicles.
So it had to navigate a tight space,
Yeah.
make multiple adjustments, really think through the process.
Exactly.
Yeah.
And here's the kicker.
Okay.
DiMA had never been specifically trained on three-point turns.
Wow.
It was a completely new scenario.
Okay.
A true test of its ability to generalize its knowledge
Yeah.
and apply it to a novel situation.
And it passed with flying colors.
It did. DiMA was able to successfully execute the three-point turn, demonstrating a level of adaptability and problem-solving that's rarely seen in self-driving systems.
Yeah.
It's like it had learned not just specific driving maneuvers, but the underlying principles of safe and efficient driving.
Okay, I'll admit I'm starting to get pretty excited about the possibilities here.
Yeah.
But let's shift gears for a moment and talk about the bigger picture.
Sure.
What do these results mean for the future of self-driving?
Right.
Are we on the verge of seeing DiMA-powered cars on our roads soon?
DiMA is still in its early stages of development.
Okay.
But its success is a major milestone in the quest for truly intelligent and truly safe autonomous vehicles.
Right.
It's a glimpse into a future where cars can handle not just the mundane, but also the unexpected.
Right.
A future where driving becomes less stressful, more efficient, and ultimately much safer for everyone on the road.
I think that's a fantastic note to end on. Thanks for diving deep with us today.
My pleasure.
It's clear that the future of driving and the future of AI as a whole is going to be incredibly interesting to watch.
Until next time, keep those minds curious.
Yes.
And those questions coming. It sounds like DiMA's making remarkable progress. But are there any potential downsides or challenges?
Yeah, I mean, no technology is perfect.
You're absolutely right. There are always trade-offs to consider. One challenge that comes up with any complex AI system, especially one that's making life or death decisions on the road, is this issue of explainability.
Explainability. Now, that's a word I haven't heard before.
Really?
What exactly does that mean in the context of self-driving cars?
It boils down to being able to understand why an AI system made a particular decision.
Okay.
With traditional rule-based systems, it's often easier to trace back the logic and understand the reasoning behind a choice.
Right.
You can essentially follow the code, the if-then statements, and see that step-by-step process that led to a decision.
Right, because it's all laid out in a clear, predictable way.
Exactly.
But with LLMs, it's not quite as straightforward, is it?
Exactly. LLMs are trained on these massive data sets.
Yeah.
And their internal workings are so complex that it can be difficult to pinpoint exactly why they arrived at a particular conclusion.
Yeah.
It's more like a black box.
Right.
You see the input and the output, but the process in between is more opaque.
So if a DiMA-powered car makes like a sudden lane change, even if it's the right maneuver to avoid an accident, we might not fully understand why it made that decision.
That's the challenge. And in a system as critical as self-driving, where safety is paramount, being able to understand the AI's reasoning is essential, not just for debugging and improvement, but also for building trust and acceptance from both passengers and the public at large.
It seems like a bit of a paradox.
It is.
We want these systems to be intelligent and adaptable, able to make those split-second decisions that we humans sometimes struggle with.
Right.
But we also need to be able to peek inside their brains and make sure we understand their thought processes.
It's a balancing act. And it's an area of active research in the AI community. There's a growing field dedicated to developing techniques for making LLMs more transparent and interpretable. So that we can better understand not just what they're doing, but also why they're doing it.
So as this technology matures, we're not just aiming for smarter AI. We're aiming for more understandable AI.
Exactly. And that's going to be crucial for building trust. And ensuring that these systems are used responsibly and ethically.
Well, it's clear that DiMA has taken us on quite a journey today.
Yeah.
From those tricky long-tail scenarios to the ingenious way it's using language to teach cars common sense.
It is pretty cool.
It's a glimpse into a future where self-driving is not just a possibility, but a reality.
And what's truly exciting is that DiMA is just one example of the incredible innovation happening in the field of artificial intelligence.
Right.
It's a sign of how far we've come in our understanding of how machines can learn and reason. And it points to a future where AI is not just a tool, but a partner, a collaborator, helping us solve some of our most complex challenges.
I think that's a fantastic note to end on. Thanks for diving deep with us today.
My pleasure.
It's clear that the future of driving and the future of AI as a whole is going to be incredibly interesting to watch.
Until next time, keep those minds curious and those questions coming.
It sounds like DiMA is making remarkable progress.
It is.
But I'm curious, are there any potential downsides or challenges that come with this approach?
Yeah.
I mean, no technology is perfect, right?
You're absolutely right. There are always trade-offs to consider.
Okay.
One challenge that comes up with any complex AI system, especially one that's making, life or death decisions out there on the road, is this issue of explainability.
Explainability. Okay, so that's a word I haven't heard before.
Right.
What exactly does that mean in the context of self-driving cars?
It boils down to being able to understand why an AI system made a particular decision.
Okay.
With traditional rule-based systems, it's often easier to trace back the logic and understand the reasoning behind a choice. You can essentially follow the code, the if-then statements, and see the step-by-step process that led to a decision.
Right, because it's all laid out in a clear, predictable way.
Exactly.
But with LLMs, it's not quite as straightforward, is it?
Exactly. LLMs are trained on these massive data sets. And their internal workings are so complex that it can be difficult to pinpoint exactly why they arrived at a particular conclusion. It's more like a black box. You see the input and the output, but the process in between is more opaque.
So if a DiMA-powered car makes like a sudden lane change, even if it's the right maneuver, to avoid an accident, we might not fully understand why it made that decision.
That's the challenge. And in a system as critical as self-driving, where safety is paramount, being able to understand the AI's reasoning is essential. Not just for like debugging and improvement, but also for building trust and acceptance from both passengers and the public at large.
So it seems like a bit of a paradox. We want these systems to be intelligent and adaptable, able to make those split-second decisions that we humans sometimes struggle with. But we also need to be able to peek inside their brains and make sure we understand their thought processes.
It's a balancing act. And it's an area of active research in the AI community. There's this growing field dedicated to developing techniques for making LLMs more transparent and interpretable. So that we can better understand not just what they're doing, but why they're doing it.
So as this technology matures, we're not just aiming for smarter AI, we're aiming for more understandable AI.
Exactly. And that's going to be crucial for building trust and ensuring that these systems are used responsibly and ethically.
Well, DiMA has certainly taken us on quite a journey today. From those tricky long-tail scenarios to the ingenious way it's using language to teach cars common sense. It's a glimpse into a future where self-driving is not just a possibility, but a reality.
Absolutely. And what's really exciting is that DiMA is just one example of the incredible innovation that's happening in the field of artificial intelligence. It's a sign of how far we've come in our understanding of how machines can learn and reason. And it points to a future where AI is not just a tool, but a partner, a collaborator, helping us solve some of our most complex challenges.
I think that's a fantastic note to end on. Thanks for diving deep with us today.
Of course. It was a pleasure.
It's clear that the future of driving and the future of AI as a whole is going to be incredibly interesting to watch.
Until next time, keep those minds curious and those questions coming.